is going to tell us everything about cusp anomalous dimensions at strong coupling, or maybe not only at strong coupling.
Oh, I forgot to write the, okay. Talk about the quark anti-quark potential in n equal to 4 superior mirrors. So first, thank you very much for the organizer for the opportunity to speak here. Maybe in continuation to Mark's talk, here I will describe one example of quantity in n equal to 4 superior mirrors that is related to amplitudes that we are able to solve exactly. So the problem I would focus on today is the computation of the potential between a pair of quark and anti-quarks. So in QED, for example, this problem was solved by Coulomb in the 1700s. But what we are really interested is in solving this problem in QCD. Before solving it in QCD, what I'll talk about today is the same problem in n equal to 4 superior mirrors, which is our current toy model for QCD, or as Mark was discussing, the analog of the harmonic oscillator for non-abelian gauge theories. So the configuration I will focus on is the following described in this picture. Suppose we put the four-dimensional theory on an S3. So we have an S3 here times the time direction. Then we consider two static quarks and ask what is the potential between them. Since these static quarks here are placed on S3, we can put some angle in between them. Let's say one is on the north pole and the other one is related to it by some angle that I call phi here. Therefore, we'll have a static potential between this pair of quarks, which is a function of this angle. Okay. Since the theory is conformal, then by plan to a cylinder map, we can map the same configuration here of the pair of quark and anti-quark to the configuration of a Wilson line with a cusp. It's a conformal transformation that maps past infinity into the origin. And then, since the theory is conformal, the angle phi is the angle that the second line deviates from the first line. Another angle that I will use is called delta, which is pi minus phi. So such a Wilson loop would have an anomalous, would be anomalous under a change in the UV scale, in the IR scale. That is the, maybe right here, the expectation value of such a Wilson loop with a cusp would go like the UV cutoff divided by the RI cutoff to some power that I'll call gamma cusp. So the computation of this potential between the quark and the anti-quark here is the same. It's just given by this gamma cusp, which is the dependence on the scale for this operator. It's just the analog of a local operator inserted here at the origin that when we change the scale, it develops an anomalous dimension, which are called gamma cusp. Since this is a workshop on amplitudes, the same gamma cusp also appear in the computation of scattering amplitudes. Suppose one consider the process of computing some scattering amplitudes of massive particles, let's say here, K1, K2, and so on. Such a scattering amplitude is known to be exponentially suppressed due to the exchange of many soft gluons between the external on-shell states. So such an amplitude, say AN, we have a suppression factor that go like e to the minus log of the IR cutoff times, again, the same gamma cusp. So the computation of this gamma cusp is also control what is called here the Sodakov suppression factor for scattering amplitudes. To avoid any issue of signs, make clear that this factor suppress the amplitude as we try to remove the IR cutoff. And to be more precise, here we had an angle between the two pairs of quark and anti-quarks. In the same way here, when we consider the scattering process of massive particles, we will have this angle, let me call it, if we now consider these two incoming particles with some momenta, the angle between their trajectories would be a boost angle. Oops. We can analytically continue this angle phi here. So this phi would be equal to I times this var phi. And then the relation to the scattering amplitude is that cosine parabolic of this angle var phi is equal to the product of the two momenta, P1, dot P2, divided by the mass square of this particle. Okay? So computing this cusp anomalous dimension is the same as computing the Sodakov form factor, the suppression factor for the scattering amplitude of massive particles in the theory. Now, the Wilson loop we will consider here are not just the standard bosonic Wilson loop, but are supersymmetric generalization of them. These have the form, some path order exponent of the usual connection, bosonic connection, IIdx, plus a coupling to the scalars of n equal to 4 superior mills. So n equal to 4 superior mills have 6 scalars, and we can couple the Wilson line to some directions in these 6 scalars. This vector I'll call m. Wow. M dot phi. So this is the type of Wilson loop we will consider. And so when we have such a Wilson line here, it will point into some direction in the space of scalar. It will couple to one of the scalars of n equal to 4 superior mills through this coupling. Now, once we have such a cusp, once we change the geometrical angle of the Wilson loop, we could also change the direction, the scalar to which it couples to. For example, we can have one m here, and another m prime on the other line. And therefore, we can introduce a second angle, which is an internal angle between these two scalars. We'll call this angle theta, and the relation is that cosine this angle theta is equal to the product of this m and m prime. In relation to scattering amplitude, one way to give masses to the external particles is to go on the Coulomb branch of n equal to 4, to give expectation values to some of the scalars, and therefore to scatter the W bosons of this Higgs procedure. And when we give expectation value to the scalar, we don't have to give to all of them the same, to give expectation value to the same scalar. We can give expectation value in different directions, and therefore have also internal angles between the scattered particles on the Coulomb branch of n equal to 4. So also this gamma cusp for scattering amplitude is a function actually on another angle, internal angle, that I'll call theta. So this this gamma cusp in general, therefore, is a function of these two angles, phi theta, the tooth coupling, and the number of colors. And so this is the function we will focus on. We would like to compute it for any value of these parameters. In a sense, the computation of this quantity is kind of, as opposed to just computation of the spectrum of the theory, is a bit more similar to the computation of scattering amplitudes. When one has to compute a function that also depends on some kinematical data of the momenta of the scattered amplitude, and not just on the coupling. Before studying this full function, let's consider some interesting limits that we can take. Let me write it here. Some limits, interesting limits. So one limit we can take is the limit where this angle delta, I'll try to, goes to 0. This is the limit where, see this, the two Wilson lines almost backtrack on top of each other, or that the two quarks here on S3 approaching each other. In this limit, we reobtain the potential between the quark and an anti-quark in flat space. The fact that we have a sphere here when these two lines approach each other is irrelevant, and the potential between them just becomes the quark-anti-quark potential in flat space. In this case, by conformal invariance, you can show that the cusp anomalous dimension will go like, let me call it some alpha of the coupling divided by delta. or in general, you go like 1 over the distance, because the theory is conformal, between the pair of quark and anti-quark. And the interesting function to compute there is the strength of this potential is given by this alpha of lambda. Another limit that is interesting to take is the limit that this angle phi, or let me use the angle var phi, this boost angle between the quark and the anti-quark lines, goes to infinity. In this case, correspond to the scattering amplitudes of a massless particles. So the angle between these two lines is a null cusp. This is what is most known as the cusp anomalous dimension. In this case, the general form of this cusp anomalous dimension will go like linear in the angle times what I'll call gamma cusp infinity. The computation of this is what is usually called gamma cusp, but please don't confuse it with the more general cusp anomalous that we will compute here, which is a function of the two angles. This is just a limit of it. A way to think about this linear term here in the way that phi goes to infinity is like log of the spin of the operators that correspond to such lines. I will not discuss this in detail here. Just to mention that this problem was solved. It was one of the first quantities in n equal to 4 that was computed exactly for every value of the coupling, and this was done by Weisart, Eden, and Staudecker way ago. Another interesting limit that one can take is the limit where the two angles phi and theta are equal to each other up to a sign. In this case, where two angles are equal to each other, this configuration turns out to preserve some supersymmetry. So in this case, the cusp anomalous dimension, this gamma cusp, just vanish by supersymmetry. One interesting quantity to consider is the deviation away from the supersymmetric configuration. Now, since this cusp anomalous dimension vanish when the two angles are the same, to lead in order, when we turn on some small difference between the two angles, it will behave as follows. It will be equal to theta square minus phi square times another function of this angle, lambda and n. So it turns out that we can actually compute this function h, the leading deviation from the supersymmetric configuration, exactly to any value of the coupling and any number of colors. And this is using techniques that are related to localization, and this what was done in this first paper here. Let me describe it shortly. Right, because this is the limit where these two angles are the same, and just the quadratic deformation away from it. This quantity is also related to is the same as other interesting quantity. For example, the radiation, if you take a quark in n equal to 4 and accelerate it, it will radiate, and the strength of radiation of it is again computed by this function here. It's also related to what is called the two-point function of the displacement operator on a Wilson line, or what is usually called the wavy line approximation. Suppose you have a straight Wilson line, and now you're trying to deform it. Just the leading contribution is in the deformation parameter is again computed by this function h. So how do we compute it? Let me, for simplicity, since it has this form, let me, for simplicity, first set this geometrical angle to 0. So we have just a straight Wilson line that at some specific point we change the angle in the internal space. So let's suppose that one side of the angle here, we have that this m is just equal to phi 6, just coupled to one of the scalars of n equal to 4. And now when we go to the other side and consider this m prime, it will be the same as that one with a small rotation, let's say in the 5, 6 plane. So it will be given by a cosine of theta phi 6 plus sine of theta, let's say phi 5. So we have this quark here that couples to phi 6, and this quark here that couples to a linear combination of phi 5 and phi 6. Now suppose we expand it to leading order in the angle. So take the angle very close to 0, theta very close to 0. So that the 1 point function of 5, in that case will be phi 5 on the Wilson line is vanishing. The leading contribution will come from having, maybe I'll draw another picture here. So now we are at phi equal to 0. The quark and antiquarks are just sitting at the north and south pole. So these are the quarks and the antiquarks. To lead in order, we have just 2 insertions here of phi 5. Okay, again, this couples to m, and this couples to m prime. Now the 2-point function of these two phi 5 insertions, let's say phi 5 at 0 and phi 5 at some distance tau from it along this Wilson line, is just determined by conformal symmetry. And it's given by some quantity, I'll call it gamma, over cosine hyperbolic of tau minus 1. It's just you can think about it as the propagator on this cylinder. And h is just equal to gamma up to some numerical factor that comes from the integration over tau. So this is one way this is what this function h means. Now, how do we determine it using localization? So in a series of papers, first by Drucker and Gross and Eriksson, Semenoff, and Zarembo, and this was then later proved by Pestun. Consider the following. Consider just a circular Wilson loop. Okay? The expectation value of such a circular Wilson loop was computed exactly. We write it like that, and it's given by some factors. It's just given by a Bessel function. In principle, we write it exactly 2 over square root of lambda times the Bessel function I1 over square root of lambda plus 1 over n square corrections, and all. I'm just writing the leading planar contribution, but every order in this 1 over n expansion is known. And this was again proved by Pestun. This is the case for a circular Wilson loop. However, in Zarembo, consider these are 1/2 BPS Wilson loops. Zarembo consider a more general family of Wilson loops, where the circular is just 1 point in them. And for this family of Wilson loops, which are 1/4 BPS, in general, in that case, this direction that we couple to the scalar is not constant along the loop. Instead, for this kind of Wilson loop, we have that this vector m equals again to this, let's say, cosine of theta times this phi 6 plus sine theta. And here, we just rotate as we move along the loop. Let tau again be the parameter along the loop. We'll have cosine of tau, let's say phi 5 plus sine of tau phi 4. So you see that at theta equal to 0, we just have the circular Wilson loop, but as we turn on theta, we have also rotation in the internal direction. And this again preserves some part of supersymmetry. Now, this was first conjectured by Drucker and then proved by Pestun, that the expectation value of this 1/4 BPS Wilson loop as a function of the angle theta is the same as the expectation value of the circular Wilson loop, but with a different coupling, with the coupling lambda prime, where this lambda prime is just equal to lambda times cosine square of this angle theta. Okay? So suppose now we consider this type of generalized Wilson loop and expand to a very small theta. So again, as we did before, for a very small theta, we will have now an insertion on the Wilson loop of some scalar. Let me call it some phi of tau. So the computation is given by the two-point function of these two scalars now that depends on tau on this circular Wilson loop. Okay? This is the leading deviation from the circular Wilson loop when it has a very, very small angle. I'll use this one. And again, this two-point function is just determined by the conformal symmetry and is just given by the product of the two vectors times gamma divided by 1 minus cosine. Let me write it. The expectation value of these two scalars, let's say it's 0, and the tau now on the circular Wilson loop is given again by gamma times would be m of 0 dot m of tau divided by cosine of tau minus 1. And these two gammas, the one that appears here and the one that appears in our computation, must be the same, because when we take these two scalars to very close to each other, we just see a straight Wilson line with two scalar insertions. Therefore, this coefficient must be the same. On the other hand, since the expectation value of this Wilson loop is just given by the circular one with the new coupling, we can write immediately the two-point function, and we get that to lead in order, this gamma cusp is just equal to a derivative with respect to the coupling of the circular one. Just given by this theta square times some numerical factor times would be lambda d lambda of the expectation value, log the expectation value of the circular Wilson loop, which is a function of lambda, that we know any value of the coupling and any n. Okay. So we see that we managed to compute this function h. This is what it is in the case that phi equal to 0 at any value of the coupling and for any n. What happens when phi is non-zero? So if phi is non-zero, one can use just a slightly more complicated trick and use some 1/8 BPS generalization of this Wilson loop and get the full function h. I'll just mention the result here. So we will call this function here b of lambda. What you will get that for general angle phi, we get the gamma cusp is equal to, again, theta square minus phi square, as it should be, divided by 1 minus phi square over pi square, times the same function b that appears here at some other general coupling, lambda tilde, when lambda tilde is equal to lambda, again, times 1 minus phi square over pi square. Please start me if you have any questions. So this is this function h. Let me now move to the full function, to the full gamma cusp at any angle. Let's consider it in perturbation theory first. So what would be the result for this gamma cusp in perturbation theory? So for that, it's convenient to introduce a function shall call psi, just some combination of the angles. So what is this gamma cusp at weak coupling? I'll define psi to be cosine of the angle phi minus cosine of the angle theta divided by sine of the angle phi. just convenient to write the perturbative result using this parameter. So at one loop, this is just given by lambda times this psi times the angle phi. This result was first computed by, I think, Polyakov many years ago, and also by Drucker, Gross, and Oguri. For example, if you take the limit where this angle phi goes to pi, when we approach the configuration of the quark anti-quark in flat space, this result would be just twice the one in QCD, because we are coupling both to the gauge field and to the scalars. But for general angle, we get these combinations of the angles. What happened at two loops? If we now go to two loops, a two loops result was computed by Drucker and Forini. And now we have lambda square and the several terms. One term is the term linear in psi, and this is given by psi times phi as 1 minus phi square over pi square. In addition, there is a term that goes like psi square, and it multiplies some transcendental free function. For example, there are terms here that go like phi cubed, the terms that go like phi times Le2, and you can have a term that go like some Lie free. So close. So you can think about this phi as log of e to the phi as a function that carry transcendality 1. So in general, the transcendality that will sit here would be 2L minus 1. Now in the second paper, what we did is use the relation to amplitude to carry out and compute this cusp anomalous dimension to free loops. And what happened at free loops? The free loop is the following. We have minus lambda cubed now. You get the term linear in psi, with psi times phi, times this piece we already know. Know that when the angles become equal, this is go like just phi square minus theta square. So the term linear in psi is just a term we computed here already for any value of the coupling and for any n. And you see that it's just given by the only place where phi enters here is down here and in the coupling. When the only place that theta enters into this computation is for this angle psi. So this term here must be 1 minus phi square over pi square squared. Okay? And then we have a term that goes like psi square. It will have transcendental phi function like Lie 5 or in zeta, okay, zeta 3 times Le2 and so on. And finally, at free loops, you have also a term that goes like psi cube. And this psi cube multiplies what is called harmonic polylogs. Harmonic polylogs are just a generalization of polylogs. They are defined by some iterative integrals against logs with the rational coefficients. So let's write this general. These are some harmonic polylogs, zeta 5, and so on. So what we've seen before is that this term linear in psi, the first term, we know how to compute for any value of the coupling. It turns out that also this last term here, the term that has the highest power for psi, we can also compute exactly to any coupling. And this term that has the highest power for psi here is computed in a sense by a free theory. Consider the following limit. Suppose we take the coupling to 0. Again, I describe now how to compute this term that has the highest power for psi to any loop order.
I mean, what's the meaning of parameter theta in QCD?
Oh, the angle theta does not appear in QCD. It appears here when you have different scalars to couple to. Yes. This limit that I described is quite particular. I don't know or think there is analog of it in QCD, but it's special for this family of Wilson loop that has this extra second angle theta. So consider the limit when we take lambda to 0 and therefore turn off all the coupling of the theory, but at the same time we take the angle theta, or let's say I theta, to infinity. In that case, with combination of lambda times psi, we keep it fixed. That is, we keep what I'll call lambda hat, which is lambda times e to the I theta, keep this one fixed. What this limit does for us is project to ladder diagrams. Any ladder diagram that starts on one of the quark and end on the other will pick up a cosine of the angle theta because of the different angles between the two. And now we are sending I theta to infinity, so this cosine goes to infinity. At the same time, we turn off all the coupling of the theory. So this coupling of the quark to the scalars, which in general had the form square root of lambda times an integral m dot phi, so that was dt. Now, or let's say I can write it for any angle as square root of lambda over 2 integral dt times, let's say, z e to the I theta over 2 plus z bar e to the minus I theta over 2, where z is just a linear combination of two of the scalars. Let's say this z would be equal to phi 5 plus I phi 6. So now in the limit where we take this I theta to infinity, fixing the combination lambda times e to the I theta fixed, this Wilson line only couples to the z's. So we get square root of lambda hat times integral dt times z. So in principle, what the quark produces for you is just a flux of z's. This is, in a sense, an analog of what is called the BMN vacuum, the operators that are made of trace of only of z's. With that limit, only ladder diagrams contribute to the potential between the quark and the anti-quark. And ladder diagrams are much easier to sum. It turns out that computing the ladder diagram's contribution to the quark-anti-quark potential is equivalent to computing the ground state energy of just one-dimensional quantum mechanical problem. That quantum mechanical problem is the following. We have minus dx squared. Don't confuse this dx with the space-time x. This dx is, in a sense, the direction along the Wilson line, minus the potential, where the potential goes something like lambda hat divided by the propagator on the cylinder, which is cos x plus cosine of phi, plus, I would not worry about factor of 2 on pi's here, gamma cusp square of psi equal to 0. So you see the gamma cusp square is just the ground state energy of this quantum mechanical problem. This is much more simple problem to solve now. Not that for still we can solve it in perturbation theory in this lambda hat, but if we set this angle phi to 0, and then basically we turn only the internal angle, that case we can solve exactly. And what we find in that case, that this gamma cusp at phi equal to 0 is just given by 1/2 times 1 minus square root of 1 plus lambda hat square over pi square. So here is the result for any value of the coupling. And just as a curiosity, note that it's very much looking like the anomalous dimension of the fundamental excitations around the BMN vacuum. but I don't have much to say about this connection, apart from the way it looks. Let me mention another curiosity, which is the following. We can now also consider the same problem at strong coupling. You can go to strong coupling, where the computation of this cusp anomalous dimension is given by computation of some minimal surface area in ADS, and take the same limit, that is the limit that theta goes to infinity with lambda hat fixed. And in that case, we find that so first, if you look here on this quantum mechanical problem, if we take lambda to be very, very large, is go to strong coupling, then this potential is very, very big and very, very shallow in the middle. So this gamma cusp at strong coupling is just given by the value of the potential at the minimum. The kinetic energy in that case is negligible. And we care about is just the value of the potential at the minimum. You get that this gamma strong is equal to minus square root of this lambda hat. I'm just setting here x to 0 and taking the square root of that quantity divided by 2 pi cosine of phi over 2. Now, if we now go to strong coupling, the minimal surface for any angles was found by, I think, Drucker and Forini for any angles, and originally by the original paper of Maldacena, if one turns only this internal angle phi. We can go and study, again, this limit where phi goes to infinity. And we find a precise match, not just for this angular dependence and this lambda hat, but also for the factor of 2 pi. Previously, it was noted that if one resum only ladder diagrams, one gets a contribution that goes like square root of lambda at strong coupling. But the coefficient never matches, because just resumming ladder diagrams doesn't have usually a physical meaning. There is other diagrams that contribute to the quantity that may contribute at the same order. However, here we really identified a limit where the resummation of ladder diagrams gives an answer to a physical question. And therefore, in that limit, we find a precise match. I wouldn't say therefore, but in that limit, we find a precise match, not just for the behavior, but also for the coefficient. Note that the two computations did not have to match, because the limit is not the same. Here, we send lambda to 0. So this computation was done just using free theory. Where at strong coupling, we take the computation to be very, very large. So this is in principle a different limit. However, the result exactly match in this limit. This is very similar to what is known as the Frolov-Zeitlin limit for the problem of the spectrum, when one considers operators that are made of many, many Z field with only very few low momenta excitations. Also there, one finds a match between weak and strong coupling, to not just to the leading order, but also to a few order in perturbation theory. So I think this is very interesting thing to study further. I think now, after we discuss these various limits, I'll go to the main part of the talk, which is the computation of this gamma cusp for any angles in the planar limit. So this was the work in this third paper here, where we solve the problem for any value of the coupling in terms of what is called a thermodynamic beta-ansatz equations. So before describing the construction, because the computation is quite indirect, let me just present the answer. The answer is the following. It's in a sense very similar to the solution to the spectrum problem. So this is all angles. So the solution is the following. One consider a set of functions that I'll call y, or ya. Their meaning will, I hope, will be clearer in a second. And we satisfy the following equation. Log of ya, which is now a function of some parameter u, is equal to what we'll call some source phi a of u plus a convolution of some simple function k a prime with log of 1 plus y a prime. And this gamma cusp, or the energy, is equal to minus a sum of such function in integral from 0 to infinity du over 2 pi q prime, and again this log of 1 plus ya. So the place where the coupling lambda enters into these equations is here in the sources and in this convolution kernels case. So these are simple known function of what is called a spectral parameter u and the coupling lambda. And if we now turn on these angles just enter here as some linear sources like I phi and I theta, or equivalently we can just add them as the asymptotic, as a condition for how these functions behave at very, very large u. Now, this set of equations under some analytic continuation turn out to compute not only the potential between the quark and an anti-quark. We have here this pair of quark and anti-quark, but this quark and anti-quark here creates some color flux in between them, and this gamma cusp is just the energy of this color flux. This set of functions also compute all the spectrum of excitations of this flux above the vacuum. So let me try to make some sense of them and explain what these y functions actually means. So to start me, let me just review how the problem of computing the dimension of local operators in n equal to 4 super-Young-Mills was solved. And then we will apply a similar techniques for this computation. So start with this review. The spectrum, it's called the spectrum problem. So in the spectrum problem, one is interested to compute the anomalous dimension of local operators, of single trace operators. And the operator we usually start with is operator of the form of a trace of many, many z field. This is what is called the BMN operators. Again, this z is some combination of two of the scalar, let's say phi 5 plus I phi 6. This operator preserves half supersymmetry, so it doesn't get any anomalous dimension. But now one can start and insert what is called impurities. One can start and turn some of the z's into some other fields. Let's say x, which is another linear combination of two scalars. So one can consider operator with many z's, then an x, and then again many, many z's. If we now act on it with the dilatation operator, this insertion of x will start to move along the sea of z's. And what we would like to do is to find the eigenstate of the dilatation operator. This is to compute the anomalous dimension of such operators. Now the vacuum, this trace of z's, it preserves an SU2 slash 2 square of the full PSU2, 2 slash 4 symmetry of n equal to 4. The tilde here just stands for some extension of the algebra. The point that I'm trying to make using this symmetry is that this symmetry allows us to fix the dimension of such elementary excitation uniquely at any value of the coupling. And one what find is that the energy of this fundamental excitation is just given by a square root of 1 plus lambda sine square of p over 2, where p is its momentum as its move in the sea of z's. To be more precise, the symmetries tell us that it has to be of this form, where here instead of lambda there is any function of lambda, but by now we have evidence that for n equal to 4, all we have here is just the coupling lambda. So this is the energy of fundamental excitation. What happens now when we put several of these excitations together? When you put several of these excitations together, they will move and scatter with each other. And the fact that the theory is integrable means that all this scattering process factorize always into only 2 to 2 scattering. So one has to compute this the scattering matrix, let's say, of 2 of these fundamental excitations. This scattering matrix would have a matrix form, let's call it SA, AB, and a phase. Let's call it sigma, which is a function of the momenta of the 2 scattered particles. This matrix piece is just fixedly uniquely determined by the symmetry. This was first done by Weisert. It's just equal to a product of 2, what is called SU2 slash 2, we'll call it S left times S right, to SU2 slash 2 reflection matrices. And the really hard piece in computing this S matrix, the piece that is not determined by symmetry, is determined this phase factor. This phase factor is determined, I would say, almost uniquely, but what is called crossing. Crossing is the following condition. So suppose we have a particle of some momentum p and an energy E. We can do an analytic continuation into a particle that has momentum minus p and energy minus E. You should think about these particles as like holes in the Fermi sea. The crossing equation, what is called crossing, it means that if we have a pair of these particles, if we have a particle with momentum p and a cross particle which has exactly minus momentum E and minus momentum p, this is the same as having nothing. This is the same as the vacuum. Okay. And the crossing equation is the condition is that such a pair of particles scatter trivially with any other particle. So this allows us to fix this, what is called the stressing phase, this last missing piece of the scattering matrix. So once we know now both the energy of all the fundamental excitation and how they scattered, we can compute now the spectrum of any such operator in the limit where these operators are very, very large. That is the full energy or dimension of any such state is just given by the sum of the energies of all the individual excitations. But these momenta are not arbitrary, but are quantized because we have a trace, we have a closed chain. That is, when we go around the trace, when such an X excitation goes around and come back to the same position, the state must come back to itself. That is, here we have all the excitations of the chain, and now we take one excitation and taking it around back to itself, the state must come back to itself. And this gives just a quantization condition for this momenta. It depends on what are the other particles, how do we scatter with them, and what is the length of the chain. This quantization condition is what we call the beta equations. When we solve this quantization condition, we plug the momentum here, and you get the spectrum of the operators. So this is the solution of the problem when these operators are very, very large. This S matrix description of the scattering of two particles are only valid where the chain is infinitely long. But once the chain become small, and in particular of order, the loop order we are working at, we get new effects that correspond to some excitation, to some interaction that really fill the finite size of the chain and goes all the way around. So how do we solve for the spectrum of such operators in the limit or for any length, not just very, very large chains? For that one, I have to do some trick, which was first introduced by Zamolodchikov, which is the following. Suppose we want now to study the spectrum of such operator when we have a very, very short chain. We can now compactify the time direction along a very, very long time t. Compute the partition function in this compactified time direction. It's like putting the theory in a contact with a thermal bath. In the limit where this t is very, very large, the ground state energy of this, or the partition function, is go like e to the minus t time the ground state energy. Only the ground state energy would contribute to the partition function in the limit where this time goes to infinity. Now what Zamolodchikov did is the following trick. Suppose we take this cylinder and rotate it by 90 degrees. That is, we interchange the time and the space direction along the chain. If we will do that, we'll get a very stretch, say, tori, where now the length of the time direction is L, and the length of the space direction is T. And now we have to compute the thermal partition function on these torus. Since this L is very, very small compared to T, it is very, very high temperature partition function. In that case, the result is going like e to the minus t times the free energy per unit length. What we get is that this free energy per unit length in the thermodynamic limit is just equal to the ground state energy. Now, by some analytic continuation trick, we can get not just the ground state energy, but all other excitations. And in order to compute now this free energy per unit length in the thermodynamic limit, one has to consider densities of particles. And to minimize the free energy as a function of these densities, well, these particles are constrained by the beta equations, by the quantization condition, that is, that if we take one of them around this torus, the state goes back to itself. And the result is take basically a form equivalent to the one is written there. You get it log of this YA equal to minus L times this energy. I write here mirror because this is the energy in this mirror picture, where time is what was before the space direction, plus a convolution, say A prime log of 1 plus Y A prime. And again, the energy, as before, minus the sum of an integral, again, this u over 2 pi q prime log of 1 plus ya. So note that if we turn off the, so this L is like beta in the mirror channel. It's 1 over the temperature in the mirror channel. If we turn off the coupling, we like turn off this convolution, you see that this equation becomes just the Boltzmann factors of all the particles. If we turn off the convolution, every y is just exponent of minus beta times the energy. So this is just becoming this integral dq, q is the momenta, times 1 plus e to the minus beta times the energy. It's just the Boltzmann factor, and e to the minus beta times the energy is the densities of this type of particles along the chain. when we turn on interactions, these densities are not just determined by the temperature, but they start interacting with each other. And this is what described by the convolution here. The interaction between densities of particles of different types. Okay. So you see that, for example, if one wants to study the dimension of the Konishi operator, Konishi operator is very short operator of length 4. The way it was solved was first by going through all this detour, by first solving for very, very large operators, where the result is very far from Konishi. And if you would try to compute the energy of Konishi using this beta equation, you will get a very wrong answer. And only then going through this, what is called the TBA trick, thermodynamic beta ansatz trick, and then one was able to compute the dimension of Konishi for any value of the coupling and draw really its dimension starting from weak coupling going all the way to strong coupling. The problem that we will have here for computing the potential between a pair of quark and an anti-quark is very similar to the problem of computing the dimension of Konishi. Here, however, we don't have this BMN vacuum, this series derivative, this series of these insertions. I'll use this one. Here. So here we have just a Wilson line. And you want to compute the cusp anomalous dimension. So what we will do, suppose we start from just a straight Wilson line. So we'll do is just insert this many z's here at some point along the lines. Many z's. Since these are operators that are so in the adjoint, you can put them at some point along the Wilson line. So if we now, as we did before, if we now turn one of these z's, let's say, into an x, and we act on this Wilson line with the dilatation operator, it will exactly in the same way start to move along the c's of z's. The only new feature is now that when we go here to the end, we are not taking a trace, but we have here the Wilson line. If this Wilson line coupled to some other scalar, which is not one of the scalars that introduce the z's, this configuration is still BPS. So the configuration, what we call our vacuum, that we have just z's inserted along the loop, have 0 cusp anomalous dimension. And when we insert these x's, it's like describing the excitations of this flux. They will start to move. And when they get here to the boundary, to the Wilson line, they will be reflected and going back. So let me first discuss the symmetry. So here we have operators on a Wilson line. So what we first want to ask is what part of the symmetry is preserved by this Wilson line boundary now, inserted at the chain. And remember that just the C of z's, just taking a trace of z's, preserve an SU2/2 square. Introducing the Wilson line, break it to only a diagonal part, which is again just a single copy of SU2/2. We get a single copy of SU2/2, what I'll call diagonal, inside this SU2/2 square that was the symmetry of just the z's. So the boundary breaks the symmetry into only a diagonal part. Now, consider now here is the boundary, and we have some excitation, for example, this x, that is propagating and being reflected from the boundary. This propagation, this x, would have quantum numbers under both these SL2s, what I call SL2 right and SL2 left, of the original C's of Z's. So we'll have some momentum P and some index, let me call it A and B prime. And it propagates, and when it hits the boundary, it will be reflected, and we go with momentum minus P. And as we did for the S matrix, what we want now to solve is to find what is the reflection matrix for these fundamental excitations. Once we will solve for the reflection matrix of these fundamental excitations, we'll just do the analog of what we did before. We'll first consider a very, very large chains, but now with boundaries. We'll solve the problem where the limit is very, very large, and then we will do a similar trick and solve it for any size of the chain. Note that what we are particularly interested in is just the cusp anomalous dimension. It's the case where there are no z's at all. So eventually we'll take this length of the spin chain to 0. But in order to do that, we first solve the problem in a completely opposite limit, in the limit where the numbers of z's actually goes to infinity. So if we have such now a scattering problem, and you want to find what is this scattering, what is this reflection matrix, an analog of this scattering matrix that we discussed before. We can do what is called a doubling trick, and we can replace this scattering picture by just a reflection of two particles, one with momentum p and one with momentum minus p, in a single SU2/2 copy. Remember that each one of them corresponds to one of these SU2/2 copies, and once we do this doubling trick, we have only one copy of SU2/2. Sorry. Therefore, the scattering matrix is again just fixed by symmetry. The reflection matrix is again just fixed by symmetries up to a phase. You get that the reflection matrix R is A B prime is just given by the same single copy of SU2/2 matrix that we have here as A B prime times again a phase. Now it's some phase that is associated with the boundary. And again, the hard part is to determine this phase. The matrix form is again dictated completely by this symmetry. So let's do that. First, note that what I'm really doing here, I'm assuming that this boundary preserves integrability. And this is not a guarantee a priori. And eventually we'll have to test the result that we get, and we will find a match. What it means that the boundary preserves integrability? The boundary preserve, remember that for scattering matrices, preserving integrability means that the scattering of n particles factorize into only scattering particles, scattering processes of 2 to 2 cases. Similarly, if now we have a boundary and we have a pair of particles being scattering together, saying that this reflection preserve integrability means that we can change the order of the reflection processes. Is that this process is just equal to the case where first this particle was reflected and only then the other particles. So this equation will tell you that SR equal to RS. I think I missed one S. Yes. SR is called the boundary Young-Baxter equation. Here we are assuming that this reflection matrix satisfies this equation, and this allows us to determine it up to a phase. And the way to determine this phase is, again, by demanding that this pair of a particle in a hole, the one that was equivalent to the vacuum, is reflected trivially from the boundary. That is, that if we have this now a pair of one with momentum p and one with the one particle that have minus momentum and minus the energy, this scattering processes is just trivial. This is just equal to 1. And the equation that one gets is that this sigma boundary of p times sigma boundary of p bar, the crossed particle, is equal to this u plus I over 2 over u minus I over 2. So in order to solve for the reflection matrix here, what one had to do is to solve is what is called crossing equation. Let me just write down the solution, or the relevant solution for the Wilson loop problem which is the following. One write this, what is called the boundary dressing phase, as follows. Okay. So another useful set of variables is called the x's, and they are related to u by the what is called the Joukowsky map. Let me write it fast. We have x plus 1 over x. This is just definition of this variable x is equal to u over g. Okay, and what I'll use in a second, I'll call x plus or minus of u. This is defined to be x at u plus or minus I over 2. And the momentum that we had before is related to x or to u in the following way, that e to the it is just equal to x plus over x minus. So this is the relation between p and u or an x at any value of the coupling. So the relevant solution for this dressing phase is the following. We find that this dressing phase, which is now a function of this x plus and x minus, you can write it as e to the I chi of x plus I chi of x minus, where this function chi of x is equal, at least for x that is bigger than 1, for the following contour integral at z equal to 1 dz over 2 pi I of 1 over x minus z times a log of sinh 2 pi g z plus 1 over z over the same thing. So once now we know what is the dressing phase, we know how any excitation of the spin chain is being reflected from the boundary. And therefore we can write the full spectrum of excitations on this spin chain with boundary in the limit where the chain is very, very large. And as we did before, the energy, or they're called the generalized cusp anomalous dimension, is given just by the sum of all the energies of the excitations, and their momentum is again quantized as follows. Here we have the two boundaries, and suppose we have now several excitations on the spin chain. We can now take one of them, translate it along the chain, let it reflect from the boundary, going back to the other chain, being reflected again, and continue. And under this process, the states must come back to itself. This gives us a generalization of the beta equation for the case that we have no boundaries. Note that this excitation is scattered with any other particles twice, once with momentum p when it goes here, and the second time with momentum minus p when it goes back. So we have this. Okay. This will give us the solution to the problem, again, when the chain is very, very large. However, we are interested just in the cusp dimension. We are interested in taking this length to 0. In order to do so, we follow the same trick that we did before. We compactify the time direction. Let me describe this. This is a generalization of the Zamolodchikov trick before. We now have not a closed chain, but a chain with a boundary. We compactified the time direction along a very, very large direction in that, but now we have here boundary to the left and some under boundary on the right. And again, the partition function is given by E minus this T times the ground state energy, or in other words, okay, is equal to E times T times what we call the generalized gamma cusp. If we now take this picture and rotate it by 90 degrees, okay, we now have a generalization of what we had before, but now the time direction is not compactified. Instead, what this boundaries reflection matrix map to is what is called two boundary states. We have one boundary state on the bottom and one boundary state on the top. And when we minimize now the partition function or the transition amplitude now between these two boundary states, this is what we get. What are the differences before is that now particles are only created in pairs of opposite momenta. And they have some amplitude for creating them, which is basically this dressing phase that I wrote here. So the form of the equation takes the same form as the one that we had for the spectrum before, because the theory here along this long chain is exactly the same theory that we have before for the local operators. The only difference is which particles we are summing here when we do this thermodynamic partition function. So the places that the dressing phase enter is here in the sources. This is some chemical potentials for these particles. And the angles, if we turn now two angles between these two boundaries, are again just entering some constant chemical potentials for the particles. Let me just now mention what tests we did for these equations. So one test we did is taking the small angle limit, the same limit that we solved before for any value of the coupling, and we solved this nonlinear equation up to free loop and found an exact match. Another thing we did is one can reproduce from this equation the exact result at one loop for any value of the angles. And this is again very non-trivially reproduced the right one loop result that it was obtained from computing Feynman diagrams. What one can do is also go to strong coupling and test these equations at strong coupling. So for example, at strong coupling, if one takes the length of this chain, L here, to be very, very large, one gets serious corrections that are exponentially suppressed in L. And one can go and solve for the minimal surface, corresponding minimal surface area, and compute this leading order correction once from this minimal area surface problem and once from this equation, and you find again an exact match also for the numerical coefficient and not just for the behavior. And finally, this dressing phase, one can study just the dressing phase at strong coupling. At strong coupling, the scattering process is given by some scattering of sine and Sinch-Gordon solitons on the worksheet. And what this dressing phase computes for you there is a time delay where the soliton is scattered from the Wilson loop boundary. And again, we find a precise match, very non-trivially, with the strong coupling limit of this dressing phase. Let me finish by mentioning future problems. There are many things to do. Just enumerate them. Let me say it by words. So at small angle, we saw that we were able to solve for this cusp anomalous dimension at any value of the coupling, and even for any value of n. And the result was extremely simple. It's just a Bessel function. One can also take this small angle limit of these nonlinear equations. They simplified in that limit, but they're still nonlinear. So there must be a way to simplify them much drastically. In a sense, what one would like to do is to teach these equations how to forget some data, because they are not describing just the cusp anomalous dimension, they're also describing the full spectrum of excitation of this flux. But if you are just interested in the cusp anomalous dimension, there should be some change of variables that simplifies them drastically. There must be, but I don't know how to do it yet. We don't understand how these densities, how this Y function behave at strong coupling in general. Strong coupling, we expect some classical description of them because this cusp is described by some classical worksheet that ends on a Wilson line with a cusp. But we don't yet understand how the solution to this equation behave in general at strong coupling. One other limit that we discussed before was the limit where this boost, when we take this angle to be a boost angle and take it to infinity. In that limit, this equation should reduce to the BS equation that computes the cusp anomalous dimension where this angle is infinite. As opposed to this equation, the BS equations are linear. And this will be obtained if one knows how these y functions behave in this limit again. It's yet to be done. For the spectrum problem, recently this infinite set of equations would reduce to a finite set. I expect that the same thing should be able to done here. These equations are basically the same, apart from the new sources and some regions of integrations. But in order to do so, one should understand more properly the analytic properties of these y functions. This solution to the crossing equation that I wrote is just one point in many other possible solutions to the crossing equations. In particular, there are some other configurations of spin chain with boundaries. For example, strings that end on d5 planes that reserve the same amount of symmetry. And therefore, the crossing equation for some of them will be exactly the same. However, the solution to the crossing equation must be different because the spectrum of these strings is different from the spectrum of strings that ends on Wilson lines. One very interesting question is, suppose we consider not the BPS, the Wilson line that are locally supersymmetric, but just a bosonic Wilson line. Does it preserve integrability? Can we carry the same program for just bosonic loop, which preserve much less symmetry? In particular, it doesn't preserve any supersymmetry.
Just delete scalar fields.
Yes. It preserves more bosonic symmetry, by the way, but it doesn't preserve any supersymmetry. One very interesting issue is that there is a theory in 3 dimensions that's called ABJM, where it's also integrable. And for example, the spectrum there was solved in exactly the same techniques. However, there, the results for integrability are uniquely determined up to some function of the coupling that is called g of lambda. The just integrability does not determine it. However, here we saw that we can obtain the same result, the result for this cusp anomalous dimension in the limit where the angle is very small, both from integrability and from localization. Localization does not suffer from this ambiguity. So we expect that this, if we will repeat this computation for ABJM, they also have a generalization of these locally supersymmetric Wilson lines, we would be able to determine this unknown function that enters the integrability by comparing the result from integrability and the result from localization for the same quantity. Yes?
Do you require some analog of the quarter BPS circle in ABGM to do that?
There are generalization.
Really? Okay.
Yes. I think that the full family of Wilson loop that I used here was not done yet, but the analog of the circular and a bit more was done.
Right. Yeah, but so my question is specifically, I mean, it seemed like in your papers you relied quite heavily on these Wilson loops on S2.
Yes.
And the analog of those kind of things where you have a scalar coupling that varies, that hasn't been done in ABGM.
Right.
So do you view that as a necessary ingredient to realize the scaling function, finding the scaling function?
Not that all we really needed is the analog of these rainbow loops that only have a 1/4 BPS, and this definitely I expect.
Yeah, I expect them to exist too.
But this
one must construct them.
Right.
Okay, that's what I was thinking. Thanks.
Thank you.
Thank you.
Any more questions?
Yes, sure.
So there are lots of conditions which go into pinning down the dressing phase,
Right.
for both the bulk S matrix and this reflection, boundary reflection. How do you know that you have, in some sense, a complete space of solutions that you're interested in and that you're picking the right one?
There is always, this is really the hardest problem of all this project, and it involves some guesswork. And we never knew that we had the right one. The only way we got confident in it that we were able to reproduce. This is what we did up to freedom computation at the small angle limit. And strong coupling and you find the agreement. But you can say that you are lucky that, in a sense, a simple solution to the crossing equation give us the Wilson loop boundary condition. So as we know, other problems have the same crossing equation but a different solution. They probably have some more complicated solution to this equation. In particular, there is actually a continuous family of them that smoothly connect between the Wilson line boundary condition and the D-brane boundary condition that involves turning on some flux on S2. And therefore, there should be some continuous family of solution to this crossing equation that interpolate between the two.
I guess that's still just some subset of all solutions.
Yes. Of course, there are infinitely many solutions. One trivial solution is not. One trivial solution is basically just taking the square root of that. But in a sense, this is the minimal solution that don't introduce new cuts. Only based on the existing cut that were already there from this Tchaikovsky map between X and U.
So just coming back to the ABJM question, so even if you had analogs of these Wilson loops, would the arguments go through in the same way? Because, for example, the connection in the Wilson loop doesn't depend linearly on the scalars, it depends quadratically on the scalars because the scalars are bifundamental, so how would you get...
I'm not saying that I know how to do it, but I'm saying that here for the first time we have a quantity that is same quantity that is computed both from integrability and from localization.
Okay, but the analogous argument for ABJM isn't completely obvious given...
Yes, this is yet to be done.
Any questions? Comments? Okay, let's thank Amit again.